Hello everyone. Let me ask you a fun question. Have you ever used a spring toy, stretched it as far as you could, only for it to snap right back? Or maybe pulled on a rubber band until it almost screamed at you to let go? Well, hidden inside these playful experiences is one of the most beautiful laws of physics, Hooke's law. For small deformations, scientists noticed that stress is directly proportional to strain. In simpler words, the more you stretch, gently, not violently, the more resistance the material offers, and it does so in a perfect linear fashion. Mathematically, we write stress is proportional to strain. Here stress, sigma, represents the force per unit area, and strain, epsilon, represents the fractional deformation. As you can see in the diagram, the graph of stress versus strain starts as a neat straight line. And this line is the kingdom of Hooke's law, simple, linear, and reliable. Now let's put some numbers on that idea. Hooke's law is expressed as sigma equals k multiplied by epsilon, where sigma is the stress, epsilon is the strain, and k is the constant of proportionality. This K is called the modulus of elasticity, and it tells us how stiff or stretchy a material is. Different types of deformations give us different elastic moduli. For example, for length changes, we have Young's modulus Y, for shear deformations, we have shear modulus G, and for volume changes under pressure, we have bulk modulus K. A larger modulus means the material resists deformation strongly. Steel has a huge Young's modulus, that's why bridges are made of steel, not chocolate. Look at the table in the diagram. Stress type connects directly to strain type, and each has its own modulus. It's like matching keys to locks, perfectly paired. But wait, does Hooke's law always hold? Sadly, no. Hooke's law is an empirical law. That means it was discovered through experiments, not derived from some deeper principle. And it works beautifully, but only within a limit called the elastic limit. Up to this limit, stress and strain share a neat linear relationship. But once you cross that line, the material says, enough. I'm done obeying your math. Beyond that, the stress-strain graph bends away from linearity. Think of stretching a rubber band. At first, it stretches proportionally. Pull harder and it suddenly gets easier, or sometimes even deforms permanently. That's where Hooke's law fails. So while Hooke's law is valid for most materials under small strains, soft stuff like putty, clay, or even bubblegum never quite follow this neat rule. Alright, let's test this law with an example. Suppose we have a wire with Young's modulus equal to 2 into 10 to the power 11 pascals. The wire is stretched such that the longitudinal strain, epsilon, equals 1 into 10 to the power minus 3. We want to find the stress. Step 1. Write Hooke's law. Sigma equals y multiplied by epsilon. Step 2. Substitute the values. Sigma equals open bracket 2 into 10 to the power 11 close bracket multiplied by open bracket 1 into 10 to the power minus 3 close bracket. Step 3. Simplify. Sigma equals 2 into 10 to the power 8 pascals. That's 200 megapascals, a huge stress, typical for strong materials like steel. Look at the diagram of a wire stretched under load. The extension seems tiny, but the internal stress is massive. That's the power of Hooke's law. It lets us see the invisible forces inside solids. So, let's tie it all together. Hooke's law tells us that stress is directly proportional to strain as long as we stay within the elastic limit. The equation sigma equals k times epsilon connects these two, where k is the modulus of elasticity. Different moduli, Young's, shear, and bulk, describe how a material resists different kinds of deformation. It's important to remember that Hooke's law isn't a universal truth, it's a reliable approximation. Once a material crosses its elastic limit, the law breaks down and the material enters the plastic region. But within its limits, Hooke's law is the backbone of elasticity, engineering design, and material science. It explains why skyscrapers sway safely in the wind, why guitar strings vibrate musically, and why springs bounce back no matter how many times you pull them. I hope you now see how Robert Hooke's simple observation gave us one of the most powerful tools in physics. That's all for today's session. In the next one, we'll explore the stress-strain curve in detail and see how materials behave all the way from gentle stretching to ultimate breaking. Until then, keep stretching your curiosity, but not your wires.